Hello, it's James from XRobots.co.uk. This is part 3 of Project Ultron. The aim of this project is to build Ultron as a real robot. Because Ultron's not a costume, there's no one inside. So let's build a real robot. And I wanted to do some AI design and do some other things as well. But I also wanted to make it quite a social robot, so that basically it can interact with people at exhibitions and places that I exhibit at. So last time I built a motion capture suit, which captures all of my limbs using accelerometers. It's using Adafruit Absolute Orientation sensors that just give you the angle. So you don't have to do any complicated maths to fuse all the sensors together. Each one has a gyroscope, an accelerometer and a magnetometer, and the device just gives you the angle. So I fitted 6 of those all over my body. And the aim was to try and build, to start with, a prosthetic right arm that was driven by the body language from the rest of my body. So basically when my legs are straight in the middle and they're both sort of together, then the prosthetic arm would mirror my left arm. If I put my right leg forward, as if I'm reaching, then it would almost mirror, apart from in this direction where it would do the opposite thing. And if I put my left leg forward, then it would mirror me, but instead of mirroring outwards, the right arm would track the left arm. Then the aim was to have fine tuning with head tracking. So effectively it would work quite naturally if you went to reach to pick something up, and then you could move that hand around to see what you're doing, and that could work quite well as a prosthetic. I'm not sure how well it's going to work, and in the end this is probably going to be using motion capture as a social seed as well as other sensors. So eventually I'll be 3D printing and building a sort of life-size Ultron torso, probably with 2 arms. And this is going to use all sorts of innovative mechanisms and lots of Ninja Flex rubber 3D printing filament. But before I do that, I need to try and interpret the data from the motion capture suit that I built last time. So in this episode, I'm going to build a mini prosthetic right arm. I'm going to build a mini robot arm basically, and try and control that from my left side using the motion capture suit that I built. Here's my simple robot arm design. So this is about 22 centimeters, about 8 or 9 inches tall. It's got this big blue base part, which keeps it nice and stable. And basically the red part here rotates around that, so that's just the rotational axis. We've then got a sort of upper arm, which can fold in and out, and attached to that we've got the lower part of the upper arm, which rotates, and that should give me all 3 degrees of freedom, which you have in your shoulder. Now, not quite how a shoulder works, because it's more of a ball joint. So this is kind of a crude representation just to see what I can do with the data. The actual Ultron I build full size is going to be more biologically inspired. So there's some other brackets here to hold servos. I'm using normal RC servos to control this. The only thing missing here at the moment is the actual elbow, and that needs a little bit more thinking through. So for now I'm just going to deal with the shoulder and the upper arm, and that's probably enough to get my head round as it is. So I've built the arm like this with the joints attached in that order for a specific reason, and that's to do with the type of angle that comes out of the inertial measurement unit, which are called Euler angles. So we'll look at that in a moment, but for now I'm going to print and assemble these parts and get all the servos in. Here are the first few parts that have been printed. So this is the main base here, and I've got this piece that slots on top, and that rotates quite nicely. So this was obviously printed upright on the bed, so the layers go across this way, and I left I think 0.5 millimeter between these 2 pieces, and that rotates quite nicely around there. So what we've got on the side then is a servo bracket to hold a normal RC servo, one way or the other. That's going to go on there. And then I've got this piece which I'm going to solvent weld on here in just the right place, so that that can be pushed by the servo. We've then got the upper arm, which of course goes on here, and that's pushed by another servo so that it can go outwards. And I'm just printing at the moment the bottom of this, which will rotate this way. So that gives me the rotation of your arm, essentially. Then if I was having an elbow, that would be on the bottom, which would be right down here. So that's something I'm going to think about later. And most of these joints are plastic on plastic. That one moves pretty freely. This one I've made a little hub piece that goes in the hole, which is slightly smaller, and that screws on to the holes here. So that should give me quite a lot of free motion. So I need to print a couple of extra things. I need to print some levers for the servos and so on. And we'll get that assembled and see how well it can move. So here's my development arm assembled. So we've got a servo here, which allows it to rotate. The one here is the sort of shoulder, although they're actually all shoulder axis, which allows it to go up and down. And then we've got this here, which is the upper arm that allows it to rotate that way. So as I said, I would have the elbow on here and then a wrist and so on, but for now I'm just going to do development with the upper arm. If I want to add extra parts on in the future, I can do, so I'm just going to keep this as the development arm. And obviously in the future I'll be building the full size version. It probably won't be anything like this mechanically. This is just a crude arm to get all the joints in. As I say, the real Ultron is going to be far more biologically inspired. So I'm going to control this with an Arduino Mega, which is a big Arduino with lots of I/O. That's a power supply, and this is a place to mount a breakout board for all the servo connections. And the reason I'm using the Mega is because it's got lots of UART serials on it. So I've been sending data from the motion capture suite over Bluetooth using an Arduino Uno. There is an option to use software serial on the Uno to get more serial ins and outs, but I found it doesn't work very well, so I'm using the UART serial, which is the hardware serial, which is fine for transmitting all the data because it's pretty simple, but when I'm receiving it, the UART serial is attached to the USB connector, or at least on an Uno, and that's the only hardware serial, and I really want to receive over Bluetooth to the hardware serial and still be able to talk to it with hardware serial over USB for debugging. So using this board allows me to have more than one serial interface. I can use UART serial for Bluetooth and for the connection to the PC. So that's why I'm using this. You can pick these up pretty cheap. They've got lots of pins. There's something like 44 digital I/O on there, far more than I need. We need 3 servo connections for this arm for now. So I'm going to get that wired up and we'll do a test routine and see how it moves, and then we'll start looking at the data. I'm all wired up, so I've just wired the 3 servos there to a bit of breakout board on strip board that gives them power from the 5V regulator. I've got my Bluetooth shield on here, although I'm not using it at the moment. That fits perfectly onto a Mega, the same as it does on the Uno. So let's just give that some power. I've just put a test script on the Arduino using delays and stuff from the servo sweep example. So let's just plug that in. Whoops. And then the arm should go through various motions. So that's obviously rotating. That's the Z axis, and I've labelled them, so we've got X, Z and Y on the twist there. And then it should do all of those together, which works pretty well. And cycles through them again, and that's all it's doing for now. So it's rather robotic, it's not particularly human. And one thing you'll probably notice is it looks like there's an axis missing, so let's look at that. So if you're a human, you've got 3 degrees of freedom in your shoulder, and those of course are to move your arm outwards that way, to move your arm this way, and of course to rotate it as well. So those are your 3 degrees of freedom. So it makes sense that we've got an accelerometer, gyro and magnetometer inertial measurement unit with 3 axes on, and we've got a robot arm with 3 motors on and 3 axes as well. However, you'll notice on the robot we're missing at some points an axis due to the way it's constructed. So to move my arm backwards and forwards this way, I can't actually do that. I don't have a way of rotating it this way. So it's fine when I put my arm out. So if I do this, and this is fine, then we've got rotation. So we've got rotation, and we've got rotation this way on the x-axis, which allows me to rotate my arm this way. In fact, this dummy doesn't do it, but anyway, a human can. If I turn this, I probably can. Right, like so. So what happens though when my arm's down and I can't move it this way? So here we're locked and we can't move it. Well, in fact, the answer is we sort of can, but we have to use a combination of all of the 3 of the axes. So in order to put my arm forwards, I'd have to rotate this way slightly, rotate this way slightly, and rotate this out, and move this around so my arm is facing in the right position. And then to move backwards, like this, I'd have to reverse that, and do this sort of thing, and then my arm moves in that motion. So the actual end of my arm does effectively sort of move backwards and forwards using a combination of the other axis, or at least the x-axis and the y-axis. Apart from that, everything's fine. When I put my arm out, of course, I've got the rotation there, and I've got the rotation there. And that's everything that the human can do, essentially. So let's have a talk about why it's built this way and what we get out of the inertial measurement unit. The Adafruit Absolute Orientation sensors give you results in Euler angles for X, Y and Z, which seems fairly straightforward, 3 axes for 3 degrees of freedom. But actually there's quite a lot of maths online and quite a lot of reading, and it's actually quite confusing when you first look at it. So I'm not going to go into the maths exactly, but I'm going to explain to you what I've observed comes out of one of the inertial measurement units by tilting it all around and looking at the X, Y and Z numbers. So I'm going to explain it with this box. I've written Z on there, and that's the only thing I've written on there because that's the only axis that actually stays with the box. So this is Z, so when I move my arm up and down, so that's great, and I've written Z onto that coordinate on the motor on the robot arm. Now X is rotation this way, which seems straightforward, and you'd expect that if you move in Z, then X stays with the box, right? And it does this. But that's not the case. In fact, X is now this way. So there's always rotation in space, no matter where you move the box. The result in X is always from rotating along this axis in space. That's always the case for Y as well. So if I put my arm out, so this is Y. But if I put my arm down so I vary in Z, then now this is Y, which is the same, and again it's an axis going this way in space. So that was initially very confusing, and I also found that when I moved in Y this way, I get some data out of X, even though I'm not actually rotating. And if I'm halfway between, say, 90 and 0 in Z, so about 45 degrees, and I rotate my arm, I get some data out of Y, and some out of X, and that made more sense because I'm partly rotating in X by doing this, because my arm is partly facing upwards, and I'm also partly rotating in Y. So that was really confusing for a while, and I really wanted to tether the X, Y and Z axis to the motors in the robot arm, and that's when I tried to design it, and then I worked out what's going on. So let's take that information and look at the arm again. So here's my box and here's my arm. So as I said, I'd label Z on both of them, so that makes sense. So this one will vary when I modify the position in Z. X is always rotation, so X is always rotation. Now this arm's laid out a bit funny, it's not particularly biological with the rotation axis being all the way over here. If it were directly above the shoulder, then that would be more humanoid, so it would actually rotate the arm instead of swinging it. And again, when the arm is out, then that's fine because it makes that motion of moving your arm in X still. So X always stays mechanically with rotation in space, basically. That's the aim of the design of this arm. Now Y again is this way, and that's all very well and good. And when I'm halfway between two angles, 0 and 90 in Y, then I start to get a bit of Y when I rotate, and also a bit of X. And again, if my arm was, the shoulder here rotating in X was completely in line, that would be fine because it would just make the arm turn, and I'd get sort of 50% of each axis to turn, but the result is the arm would turn to the same amount. The confusing thing was when I'm here, and I move this way, I get Y and a bit of X. But now looking at the arm, that's not so bad, because that's what I described before, where I want to turn the arm forwards, and I want to move Y at the same time to give me the effect of moving my arm like this. So that's why you get data out of X and Y when your arm is this way and you only rotate in apparently in Y. So I should be able to translate those angles directly to the motors and it roughly follow what I'm doing, and that's why I've designed the arm that way. Now it'd be nice to put in the fourth axis, although it doesn't make much sense because you don't have 4 degrees of freedom. What if I did put an axis in this way on the arm so I could actually move this way? Well, that wouldn't directly translate to Euler angles, but the sensor gives you another piece of data called quaternions, which are actually 4 pieces of data. I didn't understand that at all when I first started looking at it, but now looking at putting 4 motors into the arm, those 4 pieces of data probably make quite a lot more sense. I decided it was easier to put the motion capture stuff on this mannequin, so I've got all of those things powered up, so that's much easier for testing than me wearing it and walking around with it. I've attached the main brain there, if you like, which is the Uno with the Bluetooth transmitter and all of the connectors for the inertial measurement units. That's attached to the outside of the belt, hence these big clips, because it's easier to get to. I might design a custom belt for that. But basically, just to recap, we've got 1 sensor on the head, 1 on the body, the left arm, upper and lower, and each thigh as well. And all 6 of those are plugged in and they're transmitting their data. So on the receiving end, I've got the Mega, which will control the arm eventually. For now, I've just bridged it out, so I've bridged out ground and reset, which means the Mega's in constant reset mode, and all I'm doing is using that to receive the data over Bluetooth, and I've jumpered the serial pins the other way round so that the transmit and receive, they just get shoved basically into the USB to serial device, and the Arduino gets completely ignored and the data goes out of USB there. And that goes straight into a serial terminal, so that's all the data, X, Y and Z for all of the 6 sensors. So if I go now and shove the mannequin around a bit, you should hopefully be able to see all that data changing as it does so from all 6 sensors. So to start with, just to control those 3 axes on the arm, all we're really concerned with is the IMU on the arm there. That's one of those Adafruit sensors. That shows it's got power. So I can pull this out of its pouch and we can just trim that data out. So I need to write a sketch that takes that data, puts it into variables and echoes those back to the screen to start with, and eventually we'll tether those to the robot arm. So I'm just looking at 1 axis to start with. So I've got the transmitter here, obviously, which is Bluetooth. This is the upper arm sensor, which I've just pulled out of its pouch and I've just put there to keep it upright so it's in the right orientation. I'm now receiving over here with Bluetooth, and what I've done is jumpered the Bluetooth shield pin that would take this onto pin 1 or 0, and I've put it onto the extra serial interface, which is RX1 on the Mega, and I've now written a sketch which is reading the data from that sensor, and I've got the values being displayed on the screen here. So if I go and grab that sensor and tilt it around, we should see the last one, which is upper arm Z, moving between approximately 0, it does go further if I move it further, and all the way down to 90. Okay, and you may be to hear in the background the arm is actually attached to that as well. So now I've got my Z axis operating from that Z axis on the arm. It is constrained because it can't physically move any further, so if I keep moving nothing happens. But basically for that range of motion, this is using the accelerometer wirelessly over Bluetooth, tethered to that angle on the arm. So I just need to sort out the other 2, and then we'll have a look at some code. The code I've got here is for the receiver that controls the arm. The transmitter side is just basically taking the data straight out of the inertial measurement unit and sending them over serial, so it's doing a serial print followed by the new line character which says that's all the data. And I've trimmed that down for now just to send the data from the 3 axis from the upper arm sensor. So in my receiving code I am using the servo library. I've declared the 3 servos there. I've declared all of the values and I'm using integers. I've lost the decimal points for now. So those are all of the values for all 6 axis, all 6 sensors in their 3 axis. So I've got 2 serial interfaces being declared there. One is the default one on the board that's linked to the USB interface, and serial 1 is the extra one of 4 on the Mega, which is jumpered onto the Bluetooth receiver. And again, I've attached my 3 servos to some pins. So this is all the stuff that reads the data over Bluetooth. So it says if there's anything in the buffer, then basically go and parse int, which is getting valid integers and putting them into the 3 variables, upper arm, X, Y and Z. When it reads a new line character, it says it's finished. And then basically all I really wanted to do was stick that data straight in the servos. I've had to scale it So for Y and Z, those are the cleanest, and I basically use the map command and the constrain command there to go and get that data and constrain it and map it to the right scale to operate the servos, and then it just writes that value, and it also prints it to the serial terminal so I can see what the value is. X was a bit more complicated, and the reason for that is that when the sensor powers up, it's on sort of a 0/360 point. So in fact, the data that comes out of that is a 0 to 360 rotation. But when you tip from 0 and you keep going down, it flips over to 360, which is quite unhelpful. And that's the point at which it powers up. It's on that point of flipping from 0 to 360. So I've had to use some logic here to turn round that 360, taking the two 180s and reversing them. So in fact it doesn't flip unless I turn it all the way around the other way, and we'll discuss what we can do about that, because of course I might move in space using the prosthetic arm, and we'd need to combine the sensor with the data with the sensor on the body to make up for that. So there's a bit of extra scaling there, but essentially that is then written out to the servo, and that's it. There's no trigonometry, there's no other angular maths or processing going on. It's pretty much taking those values over Bluetooth from the IMU and writing them out to the servos. I've set the robot arm up next to my motion capture suit, so of course these are completely wireless. We've got the Bluetooth transmitter just over here and the receivers on this board here, and I'm powering it from a battery, so this isn't linked to a PC or laptop. The USB port could be linked, but that was only for monitoring the coordinates anyway, so it is totally wireless. So I'm linked still to this IMU, which is in the arm here, which I'll just pull out. And now we should see that we've got all of the axis working. So now this is the rotation this way. So that's our Z axis. This is the Y axis, which as I tilt it will tilt, which works okay. And we've also got rotation on X. So the servo doesn't move that far. It would go all the way round on a 180 either way. I think it does about probably maybe 30 or 40 degrees each way, but that's okay. And of course all these work together. So again, we've got rotation here, staying with X in space, so that's the rotation of the arm. So that all works, and of course Z works anywhere, and I can move that round. And then we've got this other weird thing that happens that I described, where when I move this way, it tries to use all the axes. So you can see this moving and going forwards and X rotating to try and make this backwards and forwards motion, even though it doesn't have an axis in that direction. And if it could move further in X, so it could rotate further, then essentially this would be able to rotate all the way round until its arm was completely in front, and then it could put the arm up, and effectively that would be the same as my arm reaching all the way forwards. So essentially this seems to be working quite well. Of course, if I move out in Z slightly, this still works, and we should get some variation in Z as we do so. So that's actually quite a good demo there. Let me move it out slightly further, and we can still see Y rotating to try and maintain this plane. The scaling's probably not perfectly right, or maybe I'm not moving it perfectly right. That's not too bad actually, it looks about roughly the same angle. So there we go. That seems to work quite well. I've learned quite a lot by doing this piece of the project. I certainly understand Euler angles a lot better than I did when I first started looking at them. And if I move on and put the fourth axis in, I'll probably understand quaternions a bit better with this foundation. So a lot of this project is going to be R&D to build the real Ultron. It's a serious piece of robotics. And I'm going to be showing all the R&D as I go along, as I have done here. Everything down to the mechanical assemblies and everything else as well. So it's going to be quite lengthy, but hopefully quite an in-depth and interesting project. So having looked at this arm that I've actually built by looking at Euler angles and then going and working out how I would apply them to a robot, and then looking at commercial robots, I've actually found there are commercial robots that work in exactly the same way. So if you have a look at the Willow Garage PR2, which is a very expensive commercial robot that's mobile with two arms, and it does all sorts of fantastic stuff. In fact, its joint configuration is exactly the same, and it's missing that fourth axis essentially. So it would work in exactly the same way that I've described. And that probably means that it works with Euler angles. So that's really quite interesting, having done this and then discovered that that's the same. So next time I'm not sure what I'm going to work on, whether it's more robotics research. I'd actually quite like to build a piece of Ultron, so I may work on the animatronic head, but you'll have to wait till next time to find out. So don't forget to subscribe to my channel for more updates on this project and other projects, and also don't forget to check out the social media links in the description to this video.